Good afternoon. So we finally reached the beginning of the most important part of the course, after all, the integration theory. There will be lots of different types of integrals, each of them serving various purposes. Everything is, of course, with a real-life motivation behind. And teaching this class so many times already, I can give you a couple of pointers to make things more efficient and relatively easier, so to speak, as we move along. As always, it's extremely important to understand the theoretical undertaking of or the theory behind the concept. It is always far more important, at least in the beginning, to focus on the understanding of it and then postpone the computational part for later. In other words, let's worry later about integrating quickly a function of two variables, for instance. We're going to do that pretty soon, obviously. I mean, it's not like we're not going to have an example right away. But don't skip over the definition part, because everything will make so much more sense later on when we deal with different types of integrals. And when the question comes, for example, when you read a real life problem and they say, well, find the surface of this region, or find the volume of this object, or find the flux given by this fluid across the surface, you will have to know which type of tool is applicable, which is typically an integral, what type of integral, what type of coordinates to use, how to solve it, so on and so forth. But this is actually coming all the way back from understanding the concept, not the computational part. That comes actually naturally, so to speak, along the way. Now, you can make it easier if you really understood the Riemann integral in Calculus 1 and you remember how we set it up. So let's spend some time with some Calculus 1 review before we talk about the double integral. So all the way in Calculus 1, toward the end of Calculus 1, we introduced the Riemann integral for a function of a single variable over a closed interval AB. And let's focus on the definition and the default meaning of that integral. Very important, because the meaning of the integral, of course, varies, but the default meaning, I call it default because it's the meaning that comes immediately from the definition itself. So we started, if you remember, with a partition of the domain. So for simplicity, by the way, I always, when I introduce or I explain the concept of an integral, I like to show a generic function that is above the x-axis. Doesn't have to be, but we don't want to overcomplicate the matters in the beginning. Once you understand how it works in this configuration, then it should be easy to understand what happens if it's both above and below the x-axis. So the Riemann integral is nothing but a limit in the traditional sense, but the limit of a special sum obtained in the following way. You partition the domain in n equal pieces. The traditional notation is to call x0 the left-hand point of the interval, x1 the second point. In fact, let's actually take it separately here so I can see it better here. So a split in n pieces. They don't have to be equal, but let's just say they're equal. That doesn't matter in the limit in the end. And then the next one is x1, x2, somewhere in the middle, let's call it xi minus 1, xi. And traditionally, the last one, b, is also denoted by xn. So in total, we have n equal pieces, n equal segments. And then xi minus 1 xi denotes a typical piece in this partition. The distance between the nearby points sometimes is denoted by delta x. Later on, as we take the limit and we make this partition finer and finer, that means more and more points squeezed in here, with the distance between two of them shrinking to something that is close to 0. That's denoted by dx, right? Which is the reason for the notation in the integral. Okay, so then here in the function, let's say over here, this is xi minus 1 xi. Then for each segment in the partition, we pick some point in between. That doesn't have to be in the middle, but the so-called intermediate points, right, for each partition. Let's call them C1, C2, dot, 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 all the way to Ci, and the last one here will be Cn. So the way the function is sketched here in the coordinate system, let's say Ci is over here. And then we construct the so-called Riemann sum, which is a summation for which each term, so a summation where each term is made by the product between the function evaluated at the intermediate point times the distance or the length of each segment in the partition. All Riemann integrals, including the ones you're going to see in this class, doesn't matter which type of integral we're going to talk about, double, triple, curve integral or line integral, surface integral, all of these follow the same framework. You're going to take the domain, which again in calculus 1 is a segment, right? It's an interval. You will split it into non-overlapping simple pieces. In the case of an interval, those are segments, obviously. You pick an intermediate point in each piece. You evaluate the function at that point. You multiply that evaluation with the length of the segment, or more generally with the measure of that piece. Because in the case of a function of two variables, you will see that that is going to be replaced by an area of that piece. And then make a summation, right? In this case, from 1 to n. This is the so-called Riemann sum. Now, what is the default meaning for a Riemann sum of a function of a single variable? Well, the default meaning is going to be basically the area, the sum of the area of a bunch of rectangles, right? Because when I evaluate the function at the intermediate point, it's like me raising a perpendicular all the way up until it intersects the graph of the function. So that's going to be the height of the rectangle, and the width is, of course, the segment of the partition. And if I do this, notice if I do this for every single partition, it's easy to see that these rectangles, again, if we add them all together, will approximate the area between the graph of the function and the x-axis. So on and so forth, right? So this sum approximates the area between the graph and the x-axis. That area is going to be measured positively, so it's going to be positive if above x-axis and negative if below x-axis. Right? So I mean, realize that if some of the function here is below the x-axis, when you evaluate the function at that intermediate point, that f of ci will be negative, but geometrically it's still basically the height of thin rectangle, basically. So what happens if we take the limit of the Riemann sum? So if I take the limit as n goes to infinity of a Riemann sum, provided that limit exists, this limit, if it exists, we're going to call it, well, let's call it I, right? We're going to call it the integral from a to b of f of x dx. Right? So the Riemann integral, again, if it exists, if the limit exists. N goes to infinity means that these rectangles become thinner and thinner, and they will basically kind of tend in the summation to the area between the graph of the function and the x-axis. So I always like to go over this. I mean, this is obviously known, right? If you took calculus 1 seriously, you should basically know this, right? So then it begs the question, why do I spend this time in calculus 3? Because it's very important to make the analogy that it's actually the same process. So we're going to do it slower for a double integral, and then later we can basically go a little bit faster when we establish the other types of integrals. Because this process is the same for all the other integrals. And it's important to understand it's completely analogous to calculus 1. The only adaptation or difference is that obviously the shape of the domain is different, and the meaning of the function, the default meaning, is different. So one last item before we move on to the double integral itself. Why do I call it default meaning? Because obviously you're not constrained to actually evaluate just f of at ci. So you don't have to write this down because you don't want to make a clutter here. But what if instead of f of ci, let's say, I would have added up square root of 1 plus f prime of ci squared in that Riemann sum, right? Something like that. I don't know if that rings a bell, but you guys remember that there was something in calculus 2, for instance, which was related to integrating square root of 1 plus f prime squared, right? F prime of x squared. And you might remember that will give you the length or the arc length of that graph. So what you integrate or what you evaluate at that intermediate point, of course, can give you a different meaning, right? The Riemann integral is not good just for finding areas under the graph, okay? It's good for finding many other things. What that thing is, again, it depends on what you actually multiply delta x with in the Riemann sum, right? In that case, 1 plus f prime squared, if you remember, that gives you the formula for the arc length of a curve, of the graph of the function. All right, so finally, let's move on to the double integral. So for the double integral, again, in the beginning, we're going to confine ourselves to domains given by a rectangle, meaning that the function, to begin with, is going to be defined, well, as the name implies, on a rectangle. Rectangle domain simply means that you have constant bounds for both x and y. So if I were to sketch just the domain of this function, and again, just for simplicity, I'm going to show it in the positive region. Just for simplicity, it doesn't have to be there, obviously. So rectangle domain means that x varies between two constants a and b, and y between c and d. So what would be the same process like in calculus 1? Well, the domain, the rectangle, should be partitioned into equal pieces, more or less equal pieces, right? Well, equal pieces in this case will be non-overlapping rectangles, meaning that you're going to partition both a and b, both the x part from a to b and the y's from c to d, and 4 non-overlapping rectangles. So you're going to have a partition starting from x naught to xn, and somewhere in the middle here you're going to have xi minus 1 xi, just like in calculus 1. And the same thing over the y-axis. So for example, somewhere here in the middle, by the way, it doesn't have to be exactly n, so you could have, for instance, m pieces over the y-axis, like for example y naught all the way to ym, and somewhere in the middle, let's see if we can squeeze it in here, it's like you have yj minus 1 yj, right? Because we try to visualize a typical non-overlapping patch here, or rectangle, right? So again, we don't want to make too much of a clutter, but you realize that if you basically draw these vertical and horizontal lines coming from these partitions, you're going to end up the domain split into non-overlapping rectangles. Here we have to, the notation is kind of tedious if you think about, right? Because if we take this apart just to see it better, this typical piece, right, which sits between the x points x minus 1, I minus 1 xi, yj minus 1 yj. The index is I from 1 to n, j from 1 to m. So altogether, if I make this partition, I'm going to have m times n little rectangles that form the domain. All right, just like in calculus 1, we're going to pick an intermediate point. It has to have a fancier notation because notice that this intermediate point is specific to this rectangle that goes by both index I and j. So because it's also a point in the plane, we're going to call it, typically we're going to call it xi star yj star. I know it sounds a little bit tedious here, of too fancy for its own good, but there is a logic to it because the x coordinate of the intermediate point is going to be specific to xi minus 1 xi, right? So you gotta kind of have to use a similar notation. And the same thing for yj star, right? I mean, it's specific to, or in the interior of this segment, yj minus 1 yj. So it's a combination of two partitions that you have in calculus 1, basically. And you put a star on the top so that you don't confuse it, of course, with points in the partition. Apart from that, the main idea is the same. The Riemann sum in this case is going to be a double summation by I and by m, by j. What you sum up is the function evaluated at the intermediate point times the measure of the partition, of each patch in the partition. The measure in this case is going to be an area. What is the area of the rectangle? Well, it's going to be the width, which is the distance between xi minus 1, times the height, which is yj minus 1. Or you could use the shortcut delta x delta y to indicate that distance in the partition. Just like in calculus 1, as m and n going to infinity, if this double summation converges to a limit, we're going to call that limit the double integral of the function f of xy. The formal notation is going to be, well, using two integral symbols, f of xy dA. That's a formal notation, and underneath these integrals you also indicate the domain, right? This rectangle domain, let's call it D, right? So the formal notation is specified underneath the double integral symbol. So we're going to write down the formal definition on the second page, and then we'll talk about the default meaning. Then we're going to move on to computation. So stay tuned. All right, so the quick definition one more time here on the top of the page. Keep in mind this formal notation from now on. As I mentioned before, if you take my classes, you're allowed to write formulas on your formula sheet. So you create your own formula sheet. From now on, you have to be very picky by writing on the left the formal notation of each integral, and then on the right, how you compute it. We'll get to that obviously later, the computational aspect of the integral. But you have to pay attention to the logic of it, okay? Because the formal notation has some sort of logic. See, this dA indicates the element of an area, so the area element. It indicates that you in fact multiply the function, or the function evaluated at the intermediate point, by some sort of an area, right? In this case, the area of that rectangle in the limit. So just like delta x converges to dx in the limit, as you remember the calculus 1 notation, delta x delta y converges to dA, right? So a tiny area, right? As this partition becomes finer and finer, that area becomes very, very small. So it's denoted by dA. Now, what is the default meaning? This is hard to do by hand. So again, you're going to have to watch the Maple presentation at the end. but it's still important to visualize it by hand because it's still useful, I think. So if I were to sketch actually the if I were to sketch the domain, so I see along the x-axis this is A and B, this is C and D. It's somewhere in the middle here is my typical partition corresponding to delta to xi minus 1, yj minus 1 yj. So what I want you to understand here, if you evaluate the function at the intermediate point, it's analogous to raising a perpendicular over that intermediate point. So right here is f evaluated at that intermediate point. Now what happens if you multiply a height with the area of this tiny little base? Well, you form basically a tiny parallelepiped, a tiny thin box, to use a more colloquial term. Tiny thin box. And that thin box is gonna cut the surface. We're not gonna be able to sketch it here, but it's gonna cut the surface which represents the graph of the function. Some portion of this tiny box is going to be above the surface, some of it below. Just analogous to how in the single dimension case, right, for a function of a single variable, right, you had that rectangle, a portion of it could be above, a portion of it could be below the graph of the function. Same idea here, except that we have a box that is either above or below the surface, which represents the graph of the function f of xy. So that means when everything is said and done, when you add all of these thin boxes, the double integral, the default meaning of the double integral will be the volume between the graph of the function and the domain D. Again, two situations: positive if above D, the domain, and negative if below D. Completely analogous to calculus 1, except that we're talking about volumes either above or below the domain. So we're going to run the examples with Maple, but try to visualize it already. Okay, so some more portions of this graph could be above or below the x-axis. When you make that Riemann sum, you're basically constructing these non-overlapping little boxes, which when you add them up, they will approximate the volume between the graph of the function and the domain. So you already have a tool to find the volume of a solid, provided that solid is given by a function of two variables. Or put it differently, you know, if you have a hill that sits on top of a square, that's not realistic, obviously, then you can find the volume of it by simply integrating the function which represents the surface of the hill over that domain. Okay, so with that in mind, let's actually talk about how we compute it. It might be actually useful, I think, let's see. Yeah, it might be useful actually to watch the Maple presentation right now. I think it's going to be easier. And then you can continue with this. Either way is fine. I mean, as long as you visualize that this is supposed to be the volume, you can continue and then watch the presentation later. So let's make another connection with calculus 1 before we move on to other examples. I mean, to how to compute these integrals. Let's not forget that some brief sidetrack with calculus 1. Remember in calculus 1, for instance, if I gave you, for instance, a function f of x equals 5, right? Let's say a constant function. And I ask you, what's the integral from 1 to 7 of f of x dx? Right? We didn't really need calculus. Well, I mean, we kind of need calculus because we need to know the definition of the integral, but we don't need any fancy computation to figure out the answer here. Why? Well, because since we know that the integral represents the volume, of the for the area between the graph of the function and the x-axis. It happens sometimes that the shape that I try to compute has a known geometric shape, so that you don't need to actually compute it via integration. So if I graph the function f of x equals 5 between 1 and 7, let's say this is 1 and this is 7, and this is 5 over the y-axis. So the graph of the function itself is this. The integral is nothing but the area of the rectangle. I mean, the area between the graph and the x-axis, which happens to be a rectangle. So it happens to be a known geometric shape. So then I can just use geometry. I can say the area is going to be 7 minus 1, which is 6, the length of the base here, times 5 the height, which is 30. So you just can use geometry to find the integral, because it so happens that the it has a known geometric shape. In the same manner, let's say I have a rectangle given by 0 to cross 1, 3. By the way, this is another notation, typical notation for a rectangle domain. This is equivalent to stating that x is between 0 and 2 and y is between 0 and 3, right? So that's the domain called R, a rectangle. And let's say my function of two variables happens to be a constant. Let's say it's equal to square root of 2. And then the question is, what is the double integral over this domain of square root of 2 dA? So once again, you don't have to sketch, because visualization should be sufficient if you understand what goes on up until this point. But if you have to sketch it, you have a rectangle domain, once again, from 0 to 2, and then from 1 to 3. Let's see if we can sketch it. Right, that is the domain. And then the height, I mean the value of the function is root 2, but it's at the same level. That's the key thing. So if I were to sketch z equals square root of 2 as a function of x and y, it's going to be into, over a plane parallel to the xy at the level root 2. Bottom line, this is actually just a box, right, altogether. So the region below f of xy and the xy plane is just a box. So the double integral can be computed using geometry. What's the volume of a box? Well, it's the area of the base. The area of the base is 2 minus 0 times 3 minus 1 times the height, which is square root of 2. And in this case, it's 6 square root of 2. So we don't need calculus to compute, basically, or integration to compute the double integral. This is a tiny side note, to be honest. I mean, I don't find it actually it has some importance because it reinforces the default meaning of the double integral, but obviously you're not here in this class to find volumes of boxes, right? We have calculus, so we can deal with far more general shapes than that. All right, so with that, let's actually move on to the good stuff on how to compute this on the next page. All right, so obviously take a couple of minutes to sketch this before we move along. Pause my video if necessary. So before I actually make sure you have the picture sketched, this schematic before you follow me with the written part on this page. So the main tool to actually compute double integrals is the so-called Fubini's theorem. There are several versions of it, and we're going to start today obviously with the one specific to rectangle domains. So the domain, the case in which the domain is a rectangle. And it's useful to actually know briefly how it works before we actually state it. Just right off the bat, I'll tell you that the idea is basically to split the double integral into a succession of two integrals, in fact, of calculus 1 type, basically. So that's going to be the end of it in the end. But the idea is, again, to see how we can actually get an understanding of how the theorem works to compute the double integral. Again, also thinking about how we define it and the default meaning and so on and so forth. So in this picture here, we show the domain from A to B and C to D for x and y, right, over the x-axis and the y-axis. And here on the top, imagine this is basically the graph of f of xy, right? Kind of like a generic surface. Once again, it doesn't have to be on the top of the xy plane, but for easy visualization, let's think of it that way. You can compute a volume, and you kind of did this in Calculus 2. If you remember in Calculus 2, when you dealt with volumes of revolution, the main idea was to take that volume and split it into small elementary pieces. Like, for example, with the so-called, what was that? The washer, not the washer. The washer method, I think. I forgot that washer was the name for it. But anyway, like for instance, when you slice the domain in equal pieces, you know, like the washer method, right? When each piece is round, right, and you slice it just like you slice a loaf of bread, you basically integrate over each slice. So what you integrate is basically the measure or the volume in that case of each slice, and that gives you the full volume. It basically constructs a Riemann sum that represents the volume that you want to compute. For our case here, we're going to do the same thing, which we can, and I want to point out that the reason we can is because of this particular shape of the domain. If I cut it vertically with slices, let's say parallel to the y-axis, each slice can be represented by a function in the following way. So notice that this slice, again with slices parallel to the y-axis, it's basically related to a partition over the x domain, right? For a given x between a and b, if we keep it constant, let's say, the shape of each particular slice kind of looks like this. Okay, so imagine that this is actually a loaf of bread, and you cut it from above, corresponding to a fixed x between a and b. Let's actually use a different color to visualize it better. All right, so intuitively speaking, basically, if I actually integrate over the x-axis from A to B, and I integrate basically the volume of each slice, and put this in quotation marks, this should give me the double integral. All right, so this is the insight I want you to have at this point. Because remember, the double integral represents the full volume, and if I can represent, of course, each slice by the same function, I should be able to come up with the volume if I integrate each slice. When I say integrate each slice, it's really a shortcut for saying I'm going to come up with a Riemann sum over the AB interval, but what I actually add up in that Riemann sum is going to be the volume of each slice. Now the volume of each slice is going to be the area of the slice times delta x, right? It's going to be a partition over the AB, right? Over the AB interval. And of course, as I take the limit of the Riemann sum, this delta x is going to go to dx, right? It's going to approach 0 as n goes to infinity in that Riemann sum. So then the question is, how do I actually come up with the area of the slice? That's what I need. Where does that come from? Well, if I keep x constant, notice that the top here, where it cuts the surface, is nothing but the, let's call it actually s of x, right? I mean, this is basically a function of x because it's this slice is depends on the area of the slice depends on x. So starting from the beginning, the double integral of f of xy dA, I already established is going to be the integral from a to b of the area of that slice dx. But the area of that slice is really the area under this graph of the function f of xy as I keep x constant. So it's nothing but the area under the graph of this function, which is given by the integral from c to d of that function with respect to y. This is just a calculus 1 statement, right? How do you find the area between the graph of a function and its domain? The domain here is y because y varies, right? Y from c to d. Well, the area between the graph of the function and its domain is given by the Riemann integral. The only thing that's different here is that inside this parenthesis, x is constant. So for a given slice, x has a specific value. F of xy becomes a function of a single variable y. The integral from c to d therefore becomes the area of that slice. And then you're going to basically vary x, that is to say you integrate with respect to x the area of each slice. So bottom line, Fubini's theorem, this is basically what Fubini's theorem states, is that the double integral of a function of two variables over a rectangular domain is equal to an iterated integral of two Riemann integrals of calculus 1. One with respect to y, and then the result with respect to x, in that order, from the inside out. So when you compute it, you're going to do this succession of two integrals from inside out. The first is typically the harder one, depending on the case, because the first requires obviously partial integration. Because you're going to keep, in this configuration, you're going to keep x constant. And you're going to integrate with respect to y, and then the answer is going to be integrated with respect to x. Before we go to an actual example, let me actually point out that the whole reasoning that we talked about right now can be repeated if, look at the picture here on the corner, if we were to slice this this volume with slices parallel to the x-axis. So in other words, for rectangular domains, the order of integration does not matter. The same thing could be the integral from c to d, in which the innermost integral is with respect to x first, then the answer with respect to y. It's very important to realize that the order of integration can be changed in the rectangular domain, can be changed at will, because you may actually prefer strongly one way or versus the other, depending on the type of function you have. So the integration could be easier in one direction versus the other. So here you're going to keep y constant first, and you're going to do the first partial integration. And the last one is with respect to y. So with that in mind, let's continue with examples. Alright, so let's just write it one more time, the Fubini's theorem over rectangles, so we can have it in front of us. Either from A to B, and then from C to D, or shall I say from C to D first, because again it's from the inside out, or in the reverse order. First with respect to x and then with respect to y. Okay, you obviously don't have to do it in both ways, but just for the sake of it, our first example, we're going to do that, just that. in two ways. One little wrinkle before we actually move on. We learn how to do partial derivatives. We have to go now through partial integration or partial antiderivatives. The idea is the same, right? So I mean, let's say I want to compute the integral of x squared y with respect to y. You're going to keep y as a constant, and you're going to just integrate, the remaining part. Really, once you handle well the partial differentiation, the partial integration should be, or anti-differentiation should be pretty much automatic, right? The only thing is to remember to integrate versus differentiate. And then keep the other variable as a constant, one at a time. All right, so let's take our first example. Let's say we want to find the integral of the function 6x squared y minus 2x, and the domain is given by x between 0, 1, and 2, and then y between 0 and 2. All right, so let's do it in one direction. Let's say dx first. I mean the innermost one with respect to x. It's very important to pay attention not to mix up the bounds, because you solve it from the inside out and you want to do dx first, then obviously the innermost bounds are 1 and 2, right? The bounds for x. And then whatever we get here, we're going to integrate with respect to y. So slowly and steadily keep the outermost integral as it is, and now we keep y constant because we find the antiderivative with respect to x. So right now y is a constant. So I'm going to have 6y, I can pull it out as a constant, integrate with respect to x squared over 3, minus the integral of 2x, which is x squared. I like in the beginning, until I get used to the whole shenanigans here, because right now what do? You plug in the bounds of the integration, right? I like to indicate the bounds not just 1 and 2, but I like to indicate them as x equals 1 to x equals 2, to reinforce that the first integral was with respect to x. So do that in the beginning until you get used to it, obviously, because otherwise by accident you might plug in the bounds into y. But right now, again, we're still dealing with the innermost integral. So this is just calculus 1 stuff, except that you keep one variable constant. So plug in the bounds, and that means the fundamental theorem of calculus, right? This is going to be equal to whatever you get when you plug in x equals 2. So let's simplify this a little bit. 6 over 3 is 2. So 2y times 2/3 minus, I should leave some room here, minus 2 squared. And then I plug in 1, 2y times 1/3 minus 1 squared. And then whatever I'm going to get here is dy. Let's clean up that inside one more time. So I have in the end 2 times 8, that's 16y minus 4 minus quantity 2y minus 1 dy. We're going to simplify this. 16 minus 2y, that's 14y, and then minus 4 plus 1, that's minus 3. And then dy. And now we're left with the old-fashioned Riemann-1 integral from calculus 1. Antiderivative 14y squared over 2 minus 3y. And now I can write from 0 to 2, y equals 0, y equals 2, but that's the only variable left, so obviously this is for 0 and 2. So we're going to have 7 times 2 squared minus 3 times 2 minus quantity 7 times 0 squared minus 3 times 0. That's 28 minus 6 makes it 22. Again, let's do it in the other direction. I mean, in other order of integration, just to see that you end up with the same thing. Integral from 1 to 2, and then from 0 to 2, same function, but now dy first, and then dx later. You may want to actually pause the video and do this on your own. I strongly actually ask you to do that, because it's better to check your mechanics. Pause the video, do it, and then now check with me. All right, so x is a constant. We integrate with respect to y. So 6x squared, that's just a constant, and then y squared over 2 minus, again, 2x is like a constant, and then I integrate 1, right? So 2x pulls out of the integral of 1 dy, that's just y. That's the antiderivative with respect to y. So you're going to plug in the bounds for y, 0 and 2. And after that, we're going to do the last integral. So that's 3x squared, plug in 2, minus 2x times 2, 3x squared times 0 squared minus 2x times 0. You can just write 0, but I want to emphasize where it comes from, so you can get used to the mechanics. So what do I have here? I have 12x squared minus 3x squared. That makes it 12x squared. No, this is just 0. So 12x squared minus 4x dx. And then finally 12x third over 3 minus 4x squared over 2 between 1 and 2. Right, that makes it 4 times 2 squared, 2 third, minus 2 times 2 squared. And then 4 times 1 third, 2 times 1 squared. (32) minus 8 minus 4 plus 2. And obviously 34 minus 12, and obviously that's 22. Same thing. So there's more where that comes from. Just a couple of more things to talk about before we call it a day. And again, don't forget to look at the Maple presentation. Do you care about the order of integration or not? You do sometimes, very much so. Let's see. Let's look at an example. I mean, it depends on the problem at hand, obviously. But here's probably a typical example. Let's see if I'll do it completely, or maybe I'll just leave it as a cliffhanger. So for instance, and by the way, sometimes the order of integration, what is more convenient, it's not obvious until you actually do a couple of steps. So it depends on the problem. Sometimes you have to do a couple of first steps to figure out if it's one order is better than the other. But for example, let's say my function is x e to the minus xy, and the domain is let's say 0, 3, 4x and 0, 2, 4y. Do I care about the order of integration? Well, at least for the first integral, I might really like to integrate with respect to, ask yourself which one you prefer actually. pause the video and see if you have a preference. But the way I look at it, with respect to y probably is better in the beginning. Because y, if I do with respect to y first, x is a constant, and then what's left, really it's like a quick u substitution for an exponential. If I do with respect to y first, the innermost integral, it's like integrating, let's say, 5e to the minus 5y. If you imagine x is a constant, right? So it's nothing worse than this. I mean, you can do it mentally, basically. And you see what happens with the next one. Whereas if I do it with respect to x first, I have to do integration by parts, which looks kind of nasty. Not overly, but still more work. So keep this in mind. Like, I would like probably in this case again to put the y on the outside, the other way around, sorry. Put the x on the outside and do the innermost integral with respect to y first. Like that, the antiderivative with respect to y is nothing but minus e to the power minus xy. Just check yourself what happens if you differentiate this with respect to y, right? So it's a minus exponential, partial y on the top is minus x, the two minus cancel. So it's like a quick u substitution. This is going to be the integral from 0 to 3 minus e to the negative xy with the bounds for y between 0 and 2. So let's plug in 2 for y. So that's minus e to the negative 2x. And then plug in 0 for y. So that's minus e to the 0. And then you're simply left with the integral from 0 to 3 minus e to the minus 2x plus 1. Let me double check. All right. And then finally, the last integral here is going to be e to the minus 2x over 2. Differentiate that. And then plus x, the integral of 1 between 0 and 3. So when everything is said and done, I get e to the minus 6 over 2 plus 3 minus 1 over 2 plus 0, minus 1/2. So e to the minus 6 over 2 plus 5 over 2. Kind of squeeze it in here. 5 over 2. Okay, so like I said, one last remark and one quick example related to it on my last page for today's lesson. All right, so this case needs to be discussed because when it appears in practice, it's extremely, extremely useful. It makes the process of finding multiple integrals even easier. So this is a particular case of Fubini's theorem when the integral can split into a product of simple integrals, and therefore you could find the double integral by solving simultaneously the two integrals. And it tends to be even much easier, obviously. So this is the situation when the function to integrate can be written as the product between two functions, one in x and one in y. So, for example, g of x times h of y. Right? As an example, let's say, for instance, that your function to integrate is x squared times y, right, or something similar. So if you can split it into, if you can separate it, in other words, those of you who took differential equations, this is like method of separation of variables. If you can separate your function into a product, something in x, something in y, Fubini's theorem basically leads to a product of integrals in g and h. So here's the reason why. So according to Fubini, let's set up the integral with the, as always, a and b, let's say, indicates the x domain, and c and d, c to d, the y domain, right? So let's set up the integral, doesn't matter the order, but let's just set it up with the integral with respect to y first, right? The innermost one with respect to y. All right, so for the innermost one, because x is a constant with respect to y, the entire g of x is a constant with respect to y. As a constant, it can be pulled out of the innermost integral. So I can pull out of the innermost integral g of x. Okay, but now think about it. The remaining integral in terms of y now is a constant, because imagine you solve this innermost integral, you replace y with c and d, which are numbers. Again, this is, by the way, this is for rectangle domains, just to be clear here, right? We'll get to that when these are not necessarily constants. But once I replace y with c and d, this becomes another constant. And this constant, which is inside this x integral, can be pulled out of that outermost integral. And therefore, when everything is said and done, you're left basically with the product of the integral in x for the portion that depends on x with the integral in x that for the portion that depends on y. Okay, more formally, basically, if let's see one more time. So if you have to integrate from a to b and then from c to d, something like this, just make sure you pair the bounds correctly, like x is with a and b. You just basically integrate the factor that depends on x, multiply that by the factor that depends on y. This is extremely useful, especially in the case of triple integrals, which is, of course, the three-dimensional versions of this. But make sure you use it only when it's applicable, only when it factors this way. So let's finish up with the example related to this. So let's say I got to integrate this double integral. By the way, sometimes the domain is not specified, but it must be inferred from the fact that the innermost integral goes within inner bounds, right? So x is between 1 and 2, y between 0 and 1. Because this is a product of function in x and function in y, therefore this splits into a product of two integrals. The piece in terms of x, let's say in terms of y, right? From 0 to 1, and that's just y dy. And the piece in x, which is x squared dx. And then you could do, and each of them, of course, is much easier. And you could do them at the same time. So the first one is 1 over 2 minus 0. The other one, 2/3 over 3 minus 1/3 over 3. So 1 over 2 times 7 over 3 makes it 7 over 6. So those of you who take the course obviously take enough time to go over the homework, and then because this is the most important from a computational perspective, this is important because it's part of the computation of other integrals. So for example, I want to break your heart at the end now, right? But to solve a triple integral, you got to solve a double integral, right? So I mean, the double integral doesn't appear just by itself. It appears as part of the method of integration for other types of integrals. But I think that's it for today. So we'll see you next time.